Remote sensing. Lecture 3: Radiation laws. Radiation laws. The fundamental laws of radiation that affect the quantitative aspect of remote sensing techniques are only four, but of capital importance. For their determination, the most eminent European scientists of the last century were involved. They are: 1. Planck's law, which describes the trend of the power emitted by the surfaces as a function of the wavelength and their temperature. 2. Stefan Boltzmann's law, which provides the total amount of power emitted by the surfaces calculated over the entire electromagnetic spectrum as a function of their temperature. 3. Wien's law, or law of displacement, which indicates the value of the wavelength where the electromagnetic emission is maximum for a certain temperature. 4. Kirchhoff's law, which establishes the relationship between the absorption coefficients alpha and emission epsilon. Real and black body surfaces. 1. It is known that any natural surface, placed at a temperature higher than absolute zero, 0 K equals -273.1 for degrees Celsius, and therefore practically the whole physical world that surrounds us, emits electromagnetic radiations on the whole spectrum. The quantity and type of radiation emitted depend on the temperature T and on the nature of the surface of the body itself, regulated by the emissivity coefficient epsilon, which expresses the ease with which a given surface emits electromagnetic energy. There are in fact surfaces that emit energy more easily than others and which, at the same time, hold back even more easily. These surfaces are therefore strong absorbers and also, at the same time, strong emitters, or radiators. When this condition is taken to the extreme, we are in the presence of the so-called black bodies. Real and black body surfaces. 2. The characteristic of a black body, therefore, is that of having an ideal surface such that, for each given temperature T, it emits the maximum possible amount of electromagnetic energy, that is, with maximum efficiency, over the entire spectrum, and, at the same time, it is able to totally absorb the incident electromagnetic energy, whatever the wavelength. In this way, the excitance m of a black body is equivalent only to the value of the emittance, being the incident energy totally absorbed, and therefore there is not any reflection. Real and black body surfaces. 3. A black body surface, or more simply black body, is imaginable as the surface of a small opening with respect to the surface of a large isothermal rear cavity, whose internal walls do not completely reflect the radiation, P less than 1. In this way, an incident radiation, whatever its wavelength, will undergo successive absorption and reflection inside the cavity, losing energy at each reflection, as illustrated by the following figure. Real and black body surfaces. 4. If the entrance hole is small enough with respect to the size of the cavity, it is very unlikely that the trapped energy, for a kind of pot effect, will soon find the way out, and therefore comes out only after a large number of reflections, extremely damped. At this point the surface of the entrance hole is to be considered black, as it is able to absorb all the incident radiations, regardless of their wavelength and angle of incidence. For a sphere, for example, the ratio between the depth of the cavity and its opening must not be less than 10, while the minimum number of necessary internal reflections is at least 10. Real and black body surfaces. 5. From an emissive point of view, it is observed that the surface of the whole of the cavity emits a radiation that does not depend on the direction of emission, but only on its temperature T. A black body surface, or more commonly black body, is therefore a perfect radiator, and it is usually useful as a reference standard. It is an ideal surface that actually exists only with a good approximation, as can be seen from the previous figure. Real surfaces with great emissive capacity are generally spectral radiators, and that is their ability to resemble an ideal black body only holds for certain wavelength intervals. Real and black body surfaces. 6. A gray body is defined as a body whose mcg emittance, excitance, is always lower than that of a black body m of equal temperature and with the same emissive behavior at all wavelengths. If we take as reference the emittance m of a black body surface at a certain temperature T, and mcg the emittance of a gray body surface at the same temperature T, we define an emissivity coefficient epsilon, the ratio. From this definition it can be deduced that for a black body surface, epsilon equals 1, while for any other surface epsilon 1. Real and black body surfaces. 7. Furthermore, as mentioned above, the actual surfaces show an emissivity value that varies with the wavelength, so the previous equation must be written in general terms such as real and black body surfaces. 8. In the first case with epsilon equals 1, we have the ideal black body situation. In the second case, the one with epsilon 1 and constant over the whole emission spectrum, the curve represents a typical gray body, while in the last case, we have the example of a curve that represents a real surface where the emissivity varies with the wavelength remaining always less than 1. It may happen that a surface behaves differently along the spectrum, very close to a black body for certain intervals of wavelength, or of gray body in others, and of real body in others. Planck's law. 1. The general law of electromagnetic emission was enunciated by the physicist Max Planck in December 1900 after tens of years of discussions and disputes between the greatest scientists of the time. Then many more years passed before this law was completely verified and then accepted. This law is fundamental as it describes in quantitative terms the ways in which electromagnetic energy is produced, a phenomenon that applies to every surface above OK, in practice for all physical surfaces. Planck's law allows to calculate, by unit of surface area and wavelength lambda, the spectral flux density m emitted by any body, by means of the following expression, where in the following table all variables and constants are described. Planck's law. 3. Given the presence of some constants, the relationship can be rewritten in a simpler form such as where C1 and C2 are respectively. Planck's law. 4. The graphical representation of Planck's law, parametric with respect to temperatures and wavelength, or frequency, has the trend seen in the following figure, where the curves represent examples of black body surfaces, and therefore with equals 1, at different temperatures T. Planck's law. 5. To know the power emitted by the surface of any body, in a certain range of wavelengths, it is sufficient to integrate the previous equation in the chosen interval. The resulting expression is: if the emissivity is constant, the emittance will depend exclusively on the wavelength lambda and the temperature T. Stefan Boltzmann's law. 1. In order to know the overall emittance m of a physical surface on the whole electromagnetic spectrum, it is enough to integrate Planck's law on all the wavelengths of the electromagnetic spectrum, from 0 to infinity. Leaving aside the development of integrals, the resulting equation is where delta is a constant that is equal to that quantity. Stefan Boltzmann's law. 2. It is obvious that this law is valid for all the black and gray bodies that are characterized by the variation of the coefficient epsilon. For real bodies where in fact the emissivity varies with the wavelength, the previous equation must be rewritten as where MCR indicates the emittance of a real body. The following diagram shows the exponential function relating temperature and emissivity. Wien's Law 1. Another extremely useful law in remote sensing is that stated by Wien in 1893. It says that the wavelength max corresponding to the maximum electromagnetic emission of a black body surface decreases with increasing temperature T, according to the ratio. From the following figures it is clear that this function has the shape of a branch of hyperbola. For the Sun, for example, taken as a surface with an apparent black body temperature of about 6000 K, the maximum emission is around 0.5 m, yellow-green light, while bodies with temperature around 300 K, Earth's surface mean temperature, preferentially emit around 10 m. The result of this law is the choice of wavelengths and the most appropriate detection instruments to be used in remote sensing, depending on the temperature T of the surfaces under study. Kirchhoff's Law 1. Although the phenomena of interaction of electromagnetic radiation with surfaces deserve a more in-depth discussion, the specific object of a next chapter, it is important to present the aspect of energy balance that involves the study of such interactions. When electromagnetic radiation strikes any surface, three interaction mechanisms are possible. A part of the incident radiant flux I is reflected R, a part is absorbed A, and finally the remainder is transmitted T. For the principle of energy conservation we will have Kirchhoff's Law 2, for which normalizing with respect to the incident energy I is obtained. The three relationships with respect to the incident flow strictly depend on the physical nature of the surfaces and the roughness characteristics and can be defined as reflectance coefficient, absorbivity coefficient, transmissivity coefficient. Kirchhoff's Law 4. These three coefficients vary according to the chemical-physical nature of the surfaces and according to their degree of roughness or polishing. For example, a white surface and a mirror both have P equals 1, but appear different for reasons of reflection geometry, while they depend little on the temperature of the surfaces, until when, due to the temperature, the chemical characteristics do not change, physical or roughness of the surfaces themselves. Kirchhoff's Law 5. In cases where even the reflected energy is almost zero, as happens for black bodies, the relationship is simplified in the following. Epsilon equals alpha equals 1. Which is another way of expressing Kirchhoff's law and summarizes one of the fundamental concepts of radiation physics, which is essential in defining ideal blackbody surfaces. This relationship indicates how in general surfaces that absorb a lot, emit a lot, and reflect little. Kirchhoff's Law 6. It should however be noted that for real surfaces, which are neither black bodies nor gray bodies, it is always necessary to take into account the dependence of their specific coefficients on the wavelength, which should be specified from time to time. Remembering therefore the definition of the emissivity coefficient, the general equation becomes Kirchhoff's Law 6. In order to better understand the relationship between black bodies and real bodies and their basic interactions, imagine a natural surface whatever placed at an ambient temperature of 300 K. As it is intuitive, this surface will be subject to a series of interactions and the radiative processes can be summarized as follows. The surface naturally emits electromagnetic energy in accordance with Planck's law and in relation to its specific capacity of spectral emissivity. Based on its absolute temperature T and the Wien law, the maximum value of its emittant spectrum will be around 10 m wavelength, more precisely 9.66 m then in the thermal infrared region. The other neighboring bodies are in turn sources of energy, both as natural radiators and as reflectors with respect to the energy coming from other sources. The surface is affected by these irradiance flows and may show different consequent behaviors in terms of absorption, transmission, and reflection.